Okay, can we continue? Yeah, excellent. So first, thanks also for inviting me to give this guest lecture. So I'm Sara Taskinen. I'm a university lecturer here in Jyväskylä, but not in biology, but in Department of Mathematics and Statistics. And I'm going to give another kind of view of this joint species distribution modeling, but from a computational point of view. So I started working with these models while I was visiting UNSW 10 years ago, and we started looking at these models. They also do a lot of modeling with ecological applications, so that's why they were also interested in joint species distribution modeling. And since that, we have been working on this with many collaborators. For example, Jenni is somewhere here. Jenni was my student here in Jyväskylä and now is a postdoc with Otso. And Pekka is my newest student here in Jyväskylä. And then these Aussie collaborators, Francis, David, and John, they have been also working with these models. And Bert from Norway, he has been working with these models as well. So, and there are many other people involved. So, well, maybe I'll show my outline of this lecture or talk. So, after quick motivation, I will talk about extensions of GLMs, so how we formalize these models. And then I'll talk about model fitting, and now we do this in a maximum likelihood framework. So I'm not doing any Bayesian stuff here. So this is like a different what Otso is doing. Then I'll introduce this R package GLLVM. You might have heard about that. So that has Jenni has implemented all these models in that package. I'll show you one example of that and then summarize this lecture. Well, why we are doing this and what we are doing. Actually, I don't have to motivate you. This is why you are here. So many people have noticed that these kind of models, they are really useful, especially in ecology, but also in other fields of science. So if you think about your data, similar data can occur in other fields of science as well. For example, in psychology or sociology, you may have like many people and something measured from those, and then some covariates. Or so these are not only used in ecology. And I mentioned psychology or psychometry. There, these kind of models are called as generalized linear latent variable models. And we are using that framework now. And that's nothing new. So in psychometry, these kind of models were used in maybe 25 years ago. So now we are using similar models in ecology. And this kind of simple and easy to understand framework because it's just an extension of GLM. And what's nice with this latent variable modeling framework is that you can use whatever response distribution for your data. So this kind of models can handle like counts. Often you have over-dispersed counts. You can have like binary data, presence-absence data, continuous data, like some biomass maybe, or proportions data. If you have like plant cover data, percentage data. So all that can be handled in this framework. And why I think why these models haven't been used in ecology a lot since last maybe 10 years is that we haven't got any, we haven't had any efficient computational methods available. So this kind of models have been really heavy, or computationally really inefficient. But now in recent years, there have been a lot of computational tools to fit this kind of models. So we have better algorithms, we have better computers, you can use this parallel computation or supercomputers or whatever. So this is why these models are now a lot used in ecology as well. Yeah. So what I mean by extension of GLM, here's a basic GLM model, or not basic, this is for multivariate data. So I call Yij my response. So I is now, it's my row, that's like a site, and J is my column, so species in my data matrix. And if we have like, in this case, only environmental covariates, X, you can have Q of them. Then this classical multivariate GLM or stacked joint distribution model can be defined in this way. So this is how you do it in a classical way. So I have like betas, my regression coefficients, and these are now fixed. In Otto's approach, they are random, but when we do it in a maximum likelihood way, these are fixed coefficients. These were my covariates, and this beta not J is fixed species-specific intercept. So that accounts for different species totals, those column totals. And you may have heard about this package MV Append that uses this kind of multivariate GLM model. So you can fit the model using that package quite easily. There's tools for inference and visualization and others. But as you well know, this is not like a correct way to model this kind of abundance data because it doesn't take into account this correlation between species. And how that's handled in this MV Append package is that when they do inference, they use some bootstrapping in the package. So you can do it like that, but it's very slow. Or permutation tests. Well, better way to model this kind of data is, of course, to use some mixed model approach. And this is here next. My model, this mixed model is similar as before, but now we have random here, one for each site and species, and we assume that these random effects, they come from normal distribution with some covariance matrix sigma. And then if you compare to previous model, we also have in this approach this optional site or sample specific intercept to account for differences in site totals. So if you are interested in like relative abundance instead of original one, then you can add this kind of optional intercept here. So this is kind of another way or one way to model multivariate abundance data. But the problem is now that these random effects, their covariance matrix is like M times M matrix. M is my number of species. And if M is large, you have tons of parameters here to estimate. So it can be huge. And you may have used some package like LME4 or something else. And maybe notice that if you have really complex random effect there, you end up having some convergence problems. So it's a computationally really heavy model to fit. Yeah, and especially if we have like a kind of, how do you call it, fat data, so small n, large m, this kind of mixed model is difficult to fit. So this is why we prefer using this latent variable approach. So we kind of use a reduced rank sigma, so this covariance matrix. And this is why how this generalized linear latent variable model that was used in for example, psychometry 25 years ago. This is how it's formulated. So similar model as before, but instead of this Uij random effect, we have Ui transpose, where this U is my latent variable vector. And now it's not like m-dimensional, it's p-dimensional. And p can be much smaller than m, so it can be like 1 or 2 or 3, very small. And then we have lambdas. These are like factor loadings. So if you're familiar with the factor analysis, you can use that terminology here. So latent variables and factor loadings. And these are also p-dimensional. And when this p is much smaller than m, we don't have much parameters to estimate. So it's like a computationally much easier to fit than this kind of general mixed model. And yeah, we have some constraints here as well. So we assume that latent variables, they come from p-dimensional normal distribution with identity covariance matrix. This assumption is to fix the location and scale. And also this lambda matrix has some constraints. So its upper triangle is full of zeros, just to avoid it kind of rotate widely. So it fixes this constraints, fix the rotation. What if we have some trait covariates, so some information about our species? You can use similar model, but now we add here, this may look strange, but this is like a interaction term, basically. If you're familiar with normal GLMs with interactions, this is a kind of interaction in this multivariate model. Then we have main effects for environmental covariates. We don't have main effects for traits because this species-specific incept, it takes care of that. And still, this random term here or latent variable term here to take care of this correlation between species. And now you may wonder, how is this related to Otto's models? Well, basically, like I said, in our case, this beta is fixed. In Otto's model, this beta is random, comes from normal distribution, and this new expectation of that normal distribution, that includes information about traits, if you have those. If you don't have those traits, then Otto's model kind of, it's similar to this one here. And also this one reduces to, or Otto's model reduces to this one here. So they are similar. similar models. And if you remember Otto's first lecture yesterday, he talked about these research questions. So I think with these models we are having here, you can answer at least first 2 research questions. So you can have environmental coverage, trait coverage. This spatial structure can be included in some way using this alpha here. I think Jenny has implemented that, but other extensions we don't have here at the moment. But we are talking about similar models, and what's now different is how we fit the models or estimate parameters. But let me still go back to that latent variable term. So like I said, it takes care of, it accounts for this residual correlation between species, which is not accounted using those other covariates. That's why we have there. And also it represents, like Ott said, these missing predictors. So if there's some important covariates missing, that latent variable term accounts for those. Okay, our covariance matrix is still M times N matrix, like in mixed model approach. But because we have this latent variable term in our model, it is like a reduced rank matrix. So it has less parameters than in mixed model approach. And this is why it's easier to fit, or the models are easier to fit. Number of latent variables. So how many latent variables we should choose? That controls this model complexity. So of course, the more the better, but well, you have to do some trade-off between computation efficiency and model complexity. How to choose that number in practice? You can use model selection tools for that. So you can use AIC or BRC or whatever you want. And what is nice that if you choose 2 latent variables, you can plot predictions for those and get like a model-based ordination plot. And if you add your plot these estimated lambdas, so our factor loadings, we will get like a model-based biplot. And if you want to do unconstrained ordination plots, then you should check Bert van der Ven's papers or Jenny's package that includes constraint ordination as well. Okay, then some technical stuff. I hope this is not too boring for you. I talked about model fitting, and we are using maximum likelihood. How this is done in practice? Well, in practice, we are maximizing this marginal likelihood. So you can write your full likelihood as usual. And then, you know, we have these latent variables U in our model. We have to get rid of those. They are unknown, they are latent. We don't have any information about those. This is why we integrate them out. This is where this integration comes into play. And this is now a tricky point here, this integral. So if you have like a Gaussian response, like a normal model, then you can compute that integral in a closed form. But otherwise, if you have like count data or presence absence data, this can't be computed in a closed form. And that's why we need to use some computational tricks or computational methods here. But before going to that, I'll give a list of benefits of using this kind of model-based approach and the use of maximum likelihood. I think the main benefit is that you can really explicitly account for these key statistical properties of your data, especially this mean variance relationship. And that can be done using proper response distribution. So if you have count data, over-dispersed count data, you can choose proper distribution for that. Or if you have biomass data, you can take some Tweedy distribution or whatever, or some proper distribution for your percent cover data. That's one main thing. And then, of course, with model-based approach, you have all these tools I list next available. So you have like diagnostic tools. You can do some residual analysis. You have model selection tools. You can compute AIC, BIC, whatever. You have tools for statistical inference. So we know that if we compute maximum likelihood estimators, they follow normal distribution. So you can compute confidence intervals and do some testing and that kind of stuff. And use of maximum likelihood that enables fast photon emitting. That's one good point as well. Okay, but how we compute, how we maximize this marginal likelihood in practice? Well, the classical way is to use this Laplace approximation. That's, for example, what LME4 uses. So, and the point is that if you can get this marginal likelihood, if you can approximate that in a closed form, then you can fit the models quite fast and efficiently. That is what we are looking for. And this Laplace, where you approximate your likelihood in using Gaussian distribution, that's really easy to implement. And you can use it for any response distribution, any link functions. But there's one not so nice thing, and it's that it performs quite poorly if you have really discrete data. So if you have like presence absence data or like ordinal response that we usually have in psychology or psychometry, then it performs poorly. So it doesn't give like nice efficient estimators. But that's easy to use and implement. What we have used a lot is this variational approximation that origins from Bayesian computation or Bayesian statistics. There it's used like approximating posterior distribution, but here you can use it also in maximum likelihood. And the idea is, that may look bad, but idea in variational approximation is that we take our marginal likelihood, and then I just plug in this kind of a variational distribution here. So nothing illegal is done here in this first row. And then we apply this Jensen's inequality to this first row, and we get like a lower bound for our marginal likelihood. And actually this would be like, we would have like equality here if this Q variational distribution would be like a posterior for our latent variables. But instead of that, we take a tractable form. To get the tractable form for our lower bound, we apply this kind of mean field approximation. So if you have done some computational statistics, you might be familiar with this one. So we take variational distribution as a product of univariate normal distributions. And we just plug that in, and it appears that this lower bound gets this kind of equation or reduces to that kind of formula. So we kind of start from here and end up here. But still we have this integral here. That was the bad thing. And it appears that we will get this integral, we will get rid of this integral, not always, but with some distributions. For example, if we have like over-dispersed count data, we can take a special negative binomial distribution and get rid of this integral. Or if we have like a presence-absence data, and we take profit link, like Otto has done, then we get rid of this as well. But in other cases, if you take like a logic link or complementary log-log link or something else, it still appears. So this works only with very special link function and distribution combinations. And that's still not what we are looking for. So yeah, we were kind of happy, but still not fully happy, because there are still some distributions and link function combinations that don't work here. And this is why still few nasty formulas. My student Pekka started looking at this kind of approach, which is called now extended variational approach. And the idea is that we take this first term here that includes this nasty integral, and we apply second order Taylor approximation. So we approximate this term with Taylor expansion, which is given here. And when you plug that to your integral, you will get rid of that. So basically this first term here, you can always get it in a closed form. So this is how it looks like. It looks like that, and it works always. So for any distribution, for any link function, you can make this trick. Okay, and now imagine putting this last term here to our formula here. There's no integral left. There's just some terms you can easily compute. You can easily optimize that using just some like a Newton-Raphson or whatever is your favorite optimization algorithm. Okay, and finally, this model fitting is performed by maximizing this lower bound. We maximize that you simultaneously over our model parameters and these variational parameters that they included in my variational distribution. Then what is nice is that we get this estimated variational distribution that gives an approximation for our like a posterior for latent variables. So we get like predicted latent variables like as a side product here. They are given for free. And well, for inference, we can do just basic tricks. So we can take this Hessian or estimated information matrix and get like standard errors for our regression parameters. So this is how it's done in practice. To boost, Jenny didn't So what Jenny did, she implemented this using this template model builder. So that kind of boosts this computation even for. So it's like it's R package that can be used for automatic differentiation. So remember, if you optimize something, you have to compute gradients to get estimates and so on. So this TMB package does this automatically. So you just write your the function to be maximized in C++, and then call this likelihood function from R and optimize using some optimal or whatever. And standard errors are obtained as a side product. And full implementation is available in Jenny's package. And here's a list of response distributions available at the moment. So if you have like presence-absence data, we assume Bernoulli distribution. You can use either logic or profit link. They're all available. And then we have many estimation methods as well. For count data, we have Poisson, which never works. So I would forget that. But usually we have some over-dispersion. So this negative binomial, that's our favorite. And even if you wouldn't have this over-dispersion, this reduces the Poisson in that case. If we have lots of zeros, zero-inflated Poisson might be one way to go. And then for plant cover data, now we have beta available, but we are looking for more better options for that. Beta is not the best choice. For biomass, 3D is good one. Then if you have like ordinal data, you can have this multinomial profit combination, and then we have normal and non-negative continuous as well. So lots of choices to choose. Yeah, main function in Jenny's package is this GLLVM, and there's some arguments listed. So Y, that's data matrix, so your response is n times m matrix. X is matrix of environmental covariates. TR, that's your trait matrix. Then family, you can choose from this list for that. Number of latent variables, so you can try 1, 2, 3 and use AIC to choose from that. Then formula, you can pick the model using kind of similar formula that is available in GLM function. Jenny can give you details about that. Then method, so VA, EVA or LA. So which one to choose? I would say that if this VA is available, that's based on simulation studies, this is like a best option. So it's most efficient and works best. But if not, then EVA is the best, second best, and LA I would use if others are not available. Then row effect, that was the alpha term. So you can have like a fixed effect, random effect, or no effect. And initial values, so I think default is 1, but if you may have some convergence problems, and then you maybe want to try many initial values just to make sure that you end up to global optimum. So then you can make this larger, like 5 or something, and it chooses the best fit of those. And there are many more arguments you may want to check. I just in the end show one simple example how you can fit the models quite easily. This is data from Finnish Environment Institute. I call it Finnish peatland study. You know, in Finland, if you have been traveling around, you may have noticed that we have lots of peatlands here. So 1/3 of Finland is covered by this kind of really wet place. And they are highly important to Finland. So they are important for carbon storage and for water cycle and so on. And that's why they have been. There's a lot of research going on with these peatlands. And this Finnish Environment Institute, it was looking for new tools for ecological monitoring. So the idea is that these peatlands, they have been used a lot for peat mining and for forestry in recent years, or in maybe past 50 years. And now we are restoring these peatlands. So we try to make them to act like they used to be 50 years ago. And the problem is that, or the idea is that the Finnish Environment Institute wants to know if these restored peatlands, they are similar to those that are in natural condition. And that's why they are looking for these new tools for ecological monitoring. And in this paper, we studied if amoeba species can be used for ecological monitoring. So amoeba is a small kind of creature that is really abundant in this in moss samples. So if you take a sample from peatland and start looking at that in more detail, you can find lots of these amoebas there. And that's what we did here in that paper. And how data was obtained, there were actually 3 types of study sites. So we had 2 natural peatlands, 2 were used for forestry, and 2 were restored. And 15 sampling plots were taken from each site. Altogether, almost 300 moss samples were taken, and researchers identified around 50 amoeba species. And then there was some environmental coverage as well. So if we print data matrix or part of that, it looks like that. So now I have a name of peatland, land use, so natural, forestry, or restored. This site information used to take into account this kind of spatial correlation, some environmental coverage, and these are now amoeba species. So if there's some species available, there's a lot of that, and then some are quite rare. So Tyrols in some columns. So this is like a typical example of this heavily over-dispersed data. So lots of zeros, and then if you find something, there's a lot of that. Okay, Jenny fitted a latent variable model with 2 latent variables. Now p = 2, I want to do some ordination. And now this alpha here, this site effect, that's a random effect corresponding to site, just to take into account this some spatial correlation within sites. And no environmental coverage in this model because I'm doing model-based ordination. And to overcome this heavy over-dispersion in my responses, we chose negative binomial distribution. And this model can be fitted with this kind of simple script. Yeah, no X, no environmental coverage here, and 2 latent variables. And this row effect accounts this correlation within a site. Okay, for model-based ordination, you can use this ordiplot function. And for model-based biplot, you just add this argument biplot equals true in your script. And if you want to do constraint ordination, see Bert's paper. And let's see how the plots look like. So these are my model-based ordination plots. Colors are related to land use. So natural peatlands, 1 triangle for 1 peatland. They are the red ones, and the others used for forestry or restored peatlands, they are in black and blue or green. And what these ellipses here are, they are actually conditional mean squared error predictions, so like prediction regions. So we get some kind of idea how much uncertainty we have in this model-based ordination plot. Well, if we don't account for environmental coverage, you can see that there's a lot of, you can see like clusters here. And especially what's interesting is that these natural peatlands, they are different from the others what comes to species composition. I think that's the main message from this plot. And by plot here, so we have added 15 main indicator species. So if you want to see, for example, which species are important for natural peatlands, you can make this kind of by plot. And these circles or ellipses, they are like prediction regions for these indicator species. And what's next we account for environmental coverage. So we add those this X matrix to our model. So pH, water table depth and temperature into the model. Otherwise, it's similar. So now X matrix has appeared to the script. Okay, so let's see. Coef plots you these estimated regression coefficients. So if you want to check how your pH affects species abundance, you can use that Coef plot here. Information of correlation stored in factor loadings can be obtained using this get residual core matrix, and that can be used for visualization and for checking how much this environmental coverage explain your response variation. So for example, if we add these 3 environmental coverage to model, it seems that around 32% of coverage is explained with these 3 coverage. When we also use land use or land usage as a coverage, almost 50% of coverage is explained, but there's still a lot of left. And this is where we use these latent variables. So they take care of this unexplained correlation or covariation. Let's see if we have some plots here. So this is a residual correlation matrix based on this model without environmental coverage. So we can see that there are some, okay, blue is now heavy correlation. Some species are heavily correlated. This red is negative correlation. And when we account for environmental coverage, we can get rid of a lot of correlation, but there's still some left. But luckily we have these latent variables in our model to take into account this. And that was the coefficient plot I mentioned. So we get for each species and each environmental coverage this kind of plot. So we can see, for example, that there are some species. I can see a lot of questions in chat. Maybe Jenny can read those. There are some species that are heavily affected by this pH. And if this line is gray, then there's like no, they are not statistically, this effect is not statistically significant. So pH, temperature, and water table depth, this last figure here. Then I mentioned diagnostics. So if you want to plot some diagnostic plots or residual plots, you can just use plot function and get this kind of residual plots. These are now Dunn-Smith residuals, which are really nice also for discrete response. That was the model we used, negative binomial model. Nice residuals are nicely located around 0, so nothing severe seen in here. Just for comparison, we used Poisson model that doesn't take into account this overdispersion. And this is kind of residual plot that you always get if you use, for example, Poisson distribution. So it has this like a fan shape that really that's an indication of overdispersion that you should somehow take into account. And just one final point, when you fit this basic model that we use now for model-based ordination, it took maybe 15 seconds? Yes. And for full model with all environmental coverage, it was like 1 minute, so it doesn't take long to fit these models. Even if you have like a lot of species, you can have like hundreds of species or thousands, and large N. These are quite fast models to fit. Where was I? I was in a summary. Yeah, this latent variable framework that's really flexible for modeling multivariate abundance data. And in this Jenny's package, we offer quite fast methods to fit these basic models. And there's lots of tools for model checking, visualization, and inference, and so on. And these methods you can use them for quite many different types of responses, so counts, presence, absence, normal, biomass, percent cover, whatever. And you can use whatever link function you want to use or that are available. But there's a lot of work still to do. So like you have noticed, these are quite limited models, so we don't have that many yeah, there's a lot still to do. So for example, this temporal and spatial dependence that also is modeling easily. That's still something to be done, and Jenny is working on that. My student Pekka is working with this compositional data at the moment. Implementation of mixed responses, this is something, for example, psychologists really would like to have, so that your species, some would have like count data, and some would be like a presence absence data form, or ordinal in psychological applications. This is something that could be easily done, but it's someone just should do it. there's a lot of combinational solutions that you can use here. So you can, we have only looked at these variational approximation based methods, but there's others you can use, and they may be more efficient and more fast. And then you can use parallel computational techniques or some mini batching if you have like huge data and so on. And also regularization is something we are considering. And then theory for that. The theory for these estimators is still missing. I think that was my last slide. Yes. So for more details, I recommend to take a look at this GitHub page, and yeah, you can also ask questions there if something comes into your mind later. Okay, thanks. Thanks a lot. Do you have any questions here? Maybe in chat? Was there something? Oh, Jenny answered. Great. Yeah, I mean, when we are doing this, for example, this variational approximation, it's still like, it's not like full maximum likelihood method. So we are approximating this full likelihood, and theory for that is kind of well, yeah, maybe terminology was, yeah, well, I mean, kind of like if we have like full maximum likelihood estimator, we know it's large sample theory, so they are normal, estimators are normal and so on for large N. Approximation approach. We don't know if they act in a similar way. Yeah, just assume that at the moment. Any other questions? It's not.
Yeah, thanks very much, Sara.
No problem.
This kind of a complementary viewpoint to first species distribution modeling. And one thing that I'd like to discuss with me here is that from the practical point of view, people who apply choice species distribution, there is a variety of practices. So which one should you do? Mm-hmm. And I think that's a practical choice that people who apply the methods need to do. So let me first say like how I think about that, and then you can sure. Agree or disagree or complement my answer. So my first answer would be that start from the pragmatic point of view. For example, if you need to account for spatial structure or phylogeny or something like that, then you cannot apply Sara's package. You can apply our package. Then it's an obvious choice. You don't need to think anything deeper because they implement a little different features. If on the other hand, you really want to apply negative binomial distribution for your count data, you are not happy with log normal Poisson, you cannot apply our package, but you can apply Sara's package. So then that's an obvious pragmatic choice of which one to do. If it's the case that you can apply either of them, that it has the functionality, then I would say that as a very first approximation from the user's point of view, it probably doesn't matter so much which package you use. But for example, we had a master student together with Sara and Salme who was applying to the same case study, your package and our package. And of course, there are small differences in the output that we get because the methods are a little different, but by large, the kind of take-home message for the ecologists would have been, I think, the same, whichever package you would have applied. So we have in that sense, my I would say if you can apply, several of these packages to your data, they have the functionality, just apply the package that seems the most easy to use or that you are familiar already with. But then of course there are some differences, some more detailed differences, like for example we have this paper where we compared more than 30 different species distribution models, including joint and single species models, in terms of their predictive ability, that if you do cross-validation, that you partition datasets into training and test, and then you see how well the models predict the test data, then these species distribution models, they have different predictive performances. Some perform better than others, some perform better in one case study, some other in another case study. So you have this variation between them. And then if you have the time and important luxury to try different approaches, then you can also not select only between the covariance that you include in the model, but which exactly modeling framework you use to find the one that fits best your purpose. So how do you feel about this?
Yeah, I fully agree. Yeah. Agree with you. Yeah. And this computational speed and efficiency, I mean, it's if you like apply it to your data and have to do it once, it doesn't matter if you have to wait for a couple of hours. From that point of view, you don't have to necessarily use these maximum likelihood based methods. But for example, when we are comparing many different algorithms, the speed is quite crucial for us. We have to get results quickly.
Much faster than our package. For example, this masterpiece is like one benefit of your package was that it was much faster. And then the slight benefit of our package is that it gives a little bit better in predictive performance than your package.
Yeah, exactly. So you get like a smaller errors and that kind of stuff.
But in general, as I said in some earlier lecture, I'm very happy that there is this diversity of packages and groups that develop joint species distribution models, because then we have like a richer array of ideas that we can then learn from each other. And now I think very nice interaction is happening here in Taskinen, is that originally these packages were developed separately, and I guess the development remains separate, but we discuss that now, like your student Jenny is a postdoc in our group, that we can have this kind of a closer integration of packages. All right, if there are no other questions to Sara, then I think we just thank you again for visiting our course, and we move to the exercises for today. So the idea of the exercises for so that we are